Good morning. Welcome everyone to the CGD seminar. Today it's my pleasure to introduce Dr. Diandong from Curtin University, Australia. Diandong got his bachelor degree from Nanjing University of Information Science and Technology in 1990, and he got his PhD from Oklahoma University in 2004. And then he did a postdoc at the same university. Afterwards, he becomes a research scientist at the University of Texas at Austin. In 2011, he moved to the Curtin University, becomes a professor there. He has a wide research interest. He has worked on glacier and ice sheet surface mass balance modeling, landslides, and disparate flow, tropical cyclones, and extreme precipitation. Today, his talk will be our evolving understanding of extreme hydrological cycle-related natural hazards and suggestions on proactive mitigation and adaptation.
Thank you.
Yeah.
Thanks everyone for attending. Today I will give a talk about our evolving understanding of extreme hydrological cycle-related natural hazards and the suggestions on PMA. Ready? Okay. Yeah. Remember, this talk is not aiming to present answers or conclude something. I simply want to start a conversation on this important environmental topic. It would be an example of pre-exemptive adaptation and mitigation for changing environment. It's my great pleasure to share this, my research experience with like-minded colleagues here. Because it's about, it's a collaborative work, I would like to first to acknowledge all my previous mentors and collaborators during the past 20 years. I use Isher's, this photograph from Isher from 1842 because, I want to describe a seemingly disparate phenomena, natural phenomena, actually are intrinsically linked. You see the face and the goose, looks very different individually, but actually these figures emerge into each other. Yeah, because we are talking about the hydrological cycle, I would like to, give a brief review of the monumental figures in our field. From Rochway, Chani, and Balkans, and Norman Phillips. Unfortunately, have some interaction with him for a brief period of time, after coming to this country. As expected, many of them, at least these two, have direct connection with ENSO. They worked at ENSO for a long period of time before becoming our first director at the National Weather Center, CAPS, the first director, Doug Lee. This slide actually is provided by Richard, 10 years ago at the CAPS 21st anniversary, including this following slide. Actually, just told me, Richard retired like 10 years ago, long time ago, from here. But I still, remember the sweet moments, interacting with those pioneers in this research. Even 1 decade ago, we are very good at, general patterns, and even like a 5 kilometer scale, you cannot tell the difference between measurements, the left panel, and the weather prediction model. This uses ECMWF just as an example. Models here perform equally excellent. But at sub-kilometer scale, the QPF still being an issue. It's a long way to go. Many issues need to be addressed. I mentioned here is just my brief experience at the bureau. Currently simulating only the infrared information. But hopefully down the road we can assimilate more of the microwave products, so that below cloud moisture field will be better, represented in the model. So can potentially improve the weather forecasting. Also, many physical parameterization, we just realized its importance. For example, temperature-dependent eddy viscosity, their parameterization will be important for the PBL top of the vertical velocity based on the theory of the monumental work of Chani in 1963. The CISC paper, CISK paper is about their vertical velocity parameterization. You will see the importance of eddy viscosity. Also, proper installation of superfine resolution models is a problem. Right now, some European colleagues presented sub-kilometer, like a cloud resolving models. But if you seriously compare the location with reality, is a mismatch. It's a double penalty. Have errors, both spatially and phase error in temporal domain. Global pattern for, from this pattern, like an airplane, basically, or whatever you think about it looks like. Tropical ocean still, undoubtedly is a moisture source for global precipitation. There are mechanisms for the linking between tropical and mid to high latitudes. For example, we see the footprint from tropical cyclones, from typhoons, hurricanes, tropical cyclones. Also, MGO, features is this generic pattern. But I would like to say, there are also some, convoy belt mechanism, like a Pineapple Express, that's contributed to the coastal precipitation of California. I'm focusing here because natural hazards like debris flow are frequent in this region because the well-weathered slopes and also the wildfire regularly reduce the vegetation into debris. The fuel of sliding is plenty. This precipitation amount, in the globally it's insignificant, but this mechanism of transport moisture from tropical region to the coastal area is important. During the process, there are precipitation, but the moisture residue, pushed here, lifted by the local topography, give the extreme precipitation over there. Winter time, because the Mediterranean climate over there, like January, precipitation over there is significant. Like January 20th, usually around January 20th that week, there definitely will be such features bringing moisture over there. QPF is really important for natural hazard because there are two folks of the problem. One is the local topography, local geological condition, local soil and land surface condition, but also the accurate precipitation of high impact the weather system. For example, for the Hongda Mountain, eastern part of the Tibetan Plateau, we can see, the landfall of typhoon at the South China Sea will have a significant contribution to its total annual precipitation. Also, the moisture from the Indian Ocean, puts even the mountain is very high compared to what we saw here. Their mountain over there is like very impressive. But still, moisture can push through the valleys, sailing through, and provide the precipitation causing natural hazard over this region. If we look at spectrum, do a spectrum analysis of the annual precipitation, we may not find any specific returning frequency over there. But as you know, in the past 4 decades, there are significant change. You know, equivalent to 0.65 millimeter water per year increase, you know, steadily over there, likely related to the current warming of the climate. So this is just an example for looking at the regional precipitation over there. But for you know, global regions, we have made some perspective on this, and it's like take exactly a decade ago, you know, French published the perspective of even it's our perspective. Actually, I benefited from attending the U.S. Clever meeting in Berkeley. Over there, you know, I'm very proud. I made a correct projection of the ongoing Californian drought. You know, back to that time, you know, did not many colleagues did not expect it extended for 5 years long. You know, after that argument, many colleagues and I we give some deep thought and look through many researchable paper and give us some summary of this. Basically, with the intense hydrological cycle, total precipitation amount increased a little bit because there are many feedback mechanisms. Even globally, even if the even the bond ratio is holding constant from the CR relationship, convective radiation energy balance perspective, you know, the precipitation should increase, you know, to satisfy that. But there are many negative feedbacks, so the total amount of increase may be not expected as from the saturation vapor pressure point of view, the so-called Clausius-Clapeyron equation. That perspective of like 6-point increase, that's unlikely because there are negative feedbacks, you know, either from the viscosity feedback or from the fact, the polar amplification. That's a direct violation of the bond ratio constant assumption for the previous for the total precipitation to increase in the warming climate. So it will increase total precipitation, but primarily it's extreme. You know, they are clustering together. You know, there are underlying reasons. So I'm not going to have time to expand today. But if you look the relevant paper, some of them is appearing, some just past several years, including collaboration with Dr. Hu here. You will see more about the perspective on extreme precipitation. This recent one about wintertime events. You know, this you know, associated secondary flow is not the ferrule, but a part of contributing part of the ferrule cell, but it's not directly related. It's related, associated with jet secondary flow. You know, this flow is the current that push back, you know, confining the polar AMS. With polar amplification, this mechanism will be effect will diminish, and you know, more like winter storms are also likely, just like what happened in 2023 and 21 in Texas, the outbreak of the jet. Also very interesting here, we are located in a very interesting place, like low level jets provide moisture, high level provide the lifting mechanism, so it's the location of Wenka is really amazing. With that, we concluded a brief review of the hydrological cycle. What I'm focusing on today is a unified environmental modeling system segment. It's like I'm a primary coder, and I'm a hands-on scientist. I coded the code mostly, but the mentors like Robert Dickinson, you know, Lance Leslie, also other great scientists like Rong Fu, they all, and David Crowley, they all encouraged and put in a lot of effort and support in the development. Also, many students during my stay in UT Austin and OU, University of Oklahoma, they helped a lot in, because the coding is like also teamwork, yeah, I claim to be a hands-on coder, numerical coder. It's nicknamed the segment because it's scalable, extensible. I will show you very soon how extensible this is. Because in our point of view, many seemingly disparate types of storm-triggered geohazard are intrinsically interconnected. For example, one example I will show here is a progressive bobbing type of debris flow. Another is a tectonic earthquake. There, tectonic earthquake is a frictional phenomenon. It's just like a friction. We will show that if without the hydrological cycle, the dry cycle of occurrence, which is a mantle flow as a compressor, large compressor, will be very regular. It's not going to be so irregular. The irregularity previously is imposed on by the extreme precipitation. That kind of loading makes the tectonic earthquake, the frequency varies so much. But right now in the remote sensing era, all the earthquakes have a gravity field fingerprint. We can sense that from polar orbiter satellite. The more the better. With that information, we can. Right now, we have a good sense of when and where it will occur. Yeah. First, I will using achievement is not good because it's not too much achievement. The strategy is not high. All these papers, but it's a model success in some sense. I would like to say, it's being multiple times profiled by BAMS, our flagship journal in our field. Because it works perspective, close to the reality, the trend, the actual locational errors are relatively acceptable. Also, I have a monograph published also 10 years ago, more than 10 years ago. Yeah, a little bit 10 years ago. Also, we have earthquake paper is not getting well cited, but will. I'm confident it will get the attention because one expert in Canada, Curtin Wang, he we have discussions about the earthquake research using segment modeling system. The left one is 2009 Science magazine profiling of my research and some other colleagues' research after the Wenchuan earthquake. Actually, very recently, I paid a visit to Himalaya region because the upcoming collaboration with Dr. Wu here, we need that. I paid a side view here. Vegetation already covered, but some landslide scars still really apparent over there. That side is an application of segment model for very different industry, for the aviation industry. I put all the things in the Navy STOT framework. It can also handling the friction, the drag against the airplane, and with the warming climate, the drag effect, even only like 3,000 of the total fuel consumption. But considering the total volume of that industry, still sizable effects from warming climate, the fuel efficiency will be affected. Yeah, the direct publication, in landslide publication related to segment I listed here. Because, as you may also well know, in the time I was in Australia is not a good time. The research interest input from the government is very limited. Limited by that, I have to do the things required to to survive. So I do not do much of the research during, there is a gap, like a 7 years gap. I did not touch this discipline, but I still vividly remember all this stuff. First section of this talk is about debris flow and storm triggered landslide. There are different forms, landslides, overall it's a lump of solid stuff in solid shapes grading down the slope. Debris flow is like collecting the fuel first, then they flow down. But in our numerical modern system, in the Euler grade extensible system, we can handle this the same way. First, I will give a brief introduction of this phenomena, because some of colleagues here is like me, primarily atmospheric scientist. This field is not directly related to our routine research. It's basically starts the stage of the erosion process. Normally the soil is produced by oxidization, crevice of the bedrock, things like that. After many years, you accumulated a certain depth of soil. Landslides is a drastic stage of the movement, because runoff can take a bulk of that mass downslope. In addition to direct and indirect financial loss, also environmental damage. Anybody experiencing debris flow or landslide knows that. It's very tremendous, like a train passing by near you. Very amazing. Also, it brings very bad smell. That's usually the release of the rodent, inertial gas. It's poisonous gas. So things like that. It's environmental hazard in our normal lifelong time scale. Debris flows, also called mudslides, is a kind of landslide that involves saturated soil or granular material, like debris from wildfire. It's the most frequent type and also most devastating because of the flow speed. Also, it can be can translate material over extended distance. Landslide usually just spread on the mouth of the gully. Or shoot the system, but mudslide can spread, can bring big boulders long distance. Like in Malibu, there are some residents told me like a half mile away the stone originated from California. So also this type of landslide is go hand in hand with the flash flood. Precipitation, especially QPF, is an important factor for its accurate prediction. By the way, for any, not only for landslide, for any phenomena, natural phenomena, a matter of our understanding of this phenomena is if we can predict its behavior, we can claim we know it. Otherwise, we cannot fully claim it. Finally, this type of slope movement is sensitive to climate change. There are publications to support this, not my publication, but some other colleagues' publication. Also, landslides, no country, everywhere, as long as it's mountainous or hilly. Also, as long as there are liquid, liquid precipitation, extreme precipitation, it can occur. It can occur in developing countries, also can occur in advanced, much developed countries, like even here in the Asian country, USA here. In China, the China mountain is much higher than what we see here. Increased global population requires increased, the mitigation and adaptation. This is especially true for Wenchuan earthquake area. There are truly minority Chinese, truly living over there. This research review. As I just said, for any phenomena, we are like for any phenomena, we are offering with two things. One is accurate prediction, another is the efficient prediction. From very beginning, we usually go the easiest way, like using empirical measure, doing some statistics, like finding the correlation. But we cannot take a correlation as correlated. Only we all agree. Only detailed process modeling we can find the true correlative relationship. Like for climate research, we rely on GCS, reliable way climate models. It's a process model. Definitely the most advanced climate process model. We do not minimize the importance of empirical model, but we, especially for adaptation and mitigation, we need process modeling to give reliable forecasting to build our confidence, not our confidence, the general audience, their confidence. Otherwise, the measure of MP, measure of AM will not be effective enough. Yeah, here I summarize the contribution for the empirical modeling field. Yeah, also risk dimension. His brother is in our field. Also, Richard, he in 1997, in review of geophysics, a very long paper, proposed the importance of PM models. Like he anticipated the future models can simulate the full start movement, spread, cessation cycle of the detection material, having the ability to describe a wide spectrum of flow. Fortunately, our segment modeling system exactly satisfies these two requirements. Yeah, segment is not the only the process modeling, three-dimensional modeling system. There are commercial ones, Flex 3D, also 2D reduced one called triggers. It's a two-dimensional one, but it's a process modeling system. Flex 3D, I can claim, the designer is only computer scientist. They do not truly know the decomposition of stress and strain, those relationship, because they challenged me, during the process, many years ago, and I gave them some important feedback to this commercial model. Their stuff is commercial, but it's like we can design very simple modeling experiment, like mixing different sides of beads, same material, like putting on top of the slope, and how they spread, how many percentage deposit this part, that part. Segment have no difficulty because I will describe this in more detail pretty soon. But I can tell you, segment outperforms Flex 3D, 10 years ago. Right now, I'm not sure the current situation. Yeah, anything have like a two sides, pros and cons. Cons this side. Process modeling on one side, when coding it is difficult, or using it is more computer resources, demanding. Have to run on supercomputer, also called high performance field computer in Australia. I use the Texas Tech in this country. Over there, use the IVAC, right now region, after the region, there is new one, kind of my one right now. Over here, I plan to using the computer resources here if down the road need to run it. But otherwise, use this kind of personal computer you cannot run. You can run like a one column walk, but you cannot run truly three-dimensional model. It's not because the coding is difficult. The coding is simpler than numerical model, than NWP model, I should say, and the climate model. But have to run on super high resolution, like a meter, 10 meter scale for the dam, and for the bedrock stuff. And at least you have to run on basin scale, or for earthquake, this requirement is loosened, but the scale is expanded. Also, it's truly three-dimensional. So it's a need run on supercomputer. It's natural problem required, not a code set itself. Yeah, it's as I repeatedly emphasized, the wide spectrum model can handle many seemingly very different phenomena. For example, ice sheet creating, landslide, debris flow, earthquake. Also, for other application, any regular fluid, geofluid models like water flow, air flow, as long as it's not hypersonic, like subsonic and sonic, all have routines to handle. That's why commercial airplane there, even for their design, segment routines can be used. But for other advanced use, like currently I did not provide the code relevant routine. It's only for civilian use. Why three-dimensional? I should go back to our topic. It's for the need of proactive mitigation and adaptation purpose. So for that purpose, we have to use fully 3D models. The right-hand side one, in this country, in California, it's not that common. Like in China, colleagues call it a chair, like a armchair operation. But I found one case in the Black Mountain, just north of Atlanta, drive like several hours. There is a mountain called Black Mountain in the Appalachians. They have this feature, but fortunately no landslides over there. Maybe the vegetation and precipitation is plenty over there. Hurricane brings precipitation over there. Maybe hurricane already, the cold trace effect they already slided. Right now is stable. But it's such kind of patient, collective patient. Yeah. This I will summarize in the at the end. But my take-home message is that only good precipitation can establish the confidence of the the common people to believe our forecasting and warning. Otherwise, they may not take action. It's my I'm not here like it's the highest research center in our field. If I go to NCEP, even GFDR labs, over there, talking about this, they said that we already have system set up, like they show you the fancy manual type of software showing like in this case we give FEMA, this kind of advice, that kind of advice. But their core is a statistical core, like empirical relationship, like in our case is like intensity and duration of precipitation plus the local topography things, they give that kind of a correlation relationship. No one, on Earth, India, England, USA, China, it's not an issue in Australia because Australia is generally flat. The mountainous region, no people live over there, so it's not an issue for their country. Also, they have all nice, I call statistics, advanced statistics, they call neural network or whatever, AI and stuff, But their core, you said the core is the statistical one. That means, whatever fancy interface you give, but, you cannot guarantee you give like over 70% accuracy in this kind of natural hazard. But if you're using a segment modeling system, providing, taking the pins, providing the input data, using Wolf, to improve the QPF, you know, you will definitely improve the accuracy of your prediction, like over 85% right now, completely achieved for Southern California, and for China, like above 75% for the testing batch area in Hengdang Mountain, you know, the Himalaya region. You know. But that's only some they provided for whatever region. They do not give the entire, you know, dam over there. They just give sample data, and I run some testing run, you know. All these are like not recent years. It's like a decade ago when the situations are pretty amiable for collaboration. Recently, but I'm not sure how they improved. Like in NOAA, their corresponding lab, I'm not sure. Like if they actually implemented their two-dimensional process modeling system. But my suggestion, as always, will be they use process modeling to replace to at least supplement the statistical one, not to totally replace. Maybe you run both of them. Yeah, I will give some examples. You know, before giving example, I will give a brief description of the modern system. We are very familiar, so I will be very brief here. Basically, it's using the same Navy's system, also the same stencil as WORF, because I used the ARPS. I participated in the development of ARPS. WORF, like, is using the same C grade and the same modular design as I remember 20 years ago. You know, I'm familiar with Foothills lab. You know, I visited there numerous times. Yeah. Basically, you know, the numerical part you will be very familiar. The only thing I not familiar is geology. Basically, viscosity, you also call it viscosity. But for complicated material like pinch, soil, you know, mulch, I mean, and also some material, it's not that parameterization is a little bit different. So it's called rheology. Basically, it's viscosity, parameterization. Also, I should go back. Why the energy equation is also important? Because if this video is not working, I know it's not working because I put it in a hurry and make it static. It happened in Taiwan, you know. Landslides like a dream, like a steam, like a steaming ball, you know, like the vapor. What vapor? Like just you are steaming something, you are cooking something, steaming. That means, you know, the sliding against the bedrock produce a huge amount of heat. That heat is like used to evaporate this. This is only for like it's for landslide caused by earthquake because it happens for sizable region. It contributed to the falling precipitation. You know, they have like storms after earthquake in Taiwan. Also in mainland China after Wenchuan earthquake, there are big storms following. That you know, it's like a 1-2 punch to the population being affected. You know, it's making it more difficult for the activity of excavation and some other measure of saving people. Yeah, that means all these equations, the energy balance and the momentum equation, Navy's equation. Also to the left side, this S means scalar. It's not only rho. You know, for the mass conservation, we are familiar with d rho dt multiplied divergence rho e equals 0. You know, in the case of balance. But if there are sources, because during the process of debris flow, they will collect material. You know, the bunk failure, bunk not a money bunk, it's a valley bunk. They fail. They put a new material in. So that's Fe. Thomas Dunn told me use this convention. What it means for Fe, and it's a source from source. I think in this case it's a source. For the suspension in the water, it's maybe a synchrotron. Yeah. Other things we do not need to worry. It's about when you do this coding, you have to worry. But general audience, we do not need to worry. This slide is irrelevant here, but I want to show how the model are adaptable. You know, from simulating mudslide, landslide to simulating ice sheet, you change only the Glin's law. Sorry, the Glin's law of viscosity parameterization. All the other stuff are kept constant, but the boundary condition definitely need to be taken care of. But that work is measurable. That's why I also published the United States research, and that paper is cited like by 50 colleagues in the ice research field. Yeah, as I said, I use C grade just as in Wolf model, same thing. This one, is just. Robert told me to try something more illustrative for the claims paper, but eventually they do not use this figure. But anyway, I take the effort and put it here for you to see. Like basically it shows the simulation domain under the following sigma vertical coordinates. I will describe only three specialties in this modeling design, but there are some more tricky stuff. If you're interested, you can contact me. We can discuss. Or for your region of impact, there may be some other physical mechanism not currently in segment. You can also feedback, and that's welcome. During the drought, it shows it's a rice pad in Hunan, China, south of the Changjiang River. During a peak drought, the root system organized the soil around it. Shows the adaptation of the rice during extreme conditions. Also shows the root system, how they are resilience, like in our building we use like concrete, just like mud. The root system just in the iron bar inside it. Like iron, the material is strong potential stress, and the material, the soil when it's dry, similar to rock, it's like strong for compressional forces. So we learn from nature, in many aspects in our life. The Japan landslide shows the limitation of of natural vegetation. For people are right now much more powerful in fortifying a slope. They have the bulkhead much longer than root can extend. Limited by the oxygen existence in the soil, root is for the green flowering vegetation, the most common vegetation we see in our world. The vegetation is less than 1 meter deep. The fig tree in China, they said the fig tree have deeper roots. That's wrong. Fig tree have wider span of their root system. So same thing here. If the entire soil is saturated for over 1 meter, the tree and the other vegetation becomes a fuel for sliding. So it basically become a load, extra load, make the situation exacerbate the situation. Yeah, have to emphasize land surface modeling component because for collecting the debris on the slope, the most important thing is runoff. How the precipitation is distributed between runoff, infiltration, and the canopy interception. Canopy interception is very important because for medium or small rainfall, if canopy can hold the water all in the air, preventing them falling on the slope, then it's very safe, for the ground. It's very safe, no safe for sliding or debris flow, progressive bulking of that material. But for windy situation, which is rare in mountain region, wind in mountain region generally is weak, but only in some gullies they are strong, tunnel effect, calling big wind. But in case there are mechanism of making the canopy interception not effective, the land surface model become the important component. But we do not run a land surface model in the same time step to save resource computational resources. We run it on much coarser resolution, like a half an hour update the situation once. Yeah, but run the solid part of the model, not solid part, the fluid part of the sliding part, the sliding domain, I should say, using a much finer resolution, time scale resolution, like 1,000 seconds. Yeah. Also, topography, use this graded sloping in analogous to the graded sloping of the riverbed, their graded sloping. It means like it's steep, more steeper when mountain getting higher. This is not a common thing. Mountain can be any shape, some can be like a more steeper at the foothill. Some can be more, you go the higher, the steeper. This usually is like for the glacier eroded area, the big U-shaped mountain, in the Himalaya region. Also, you find it here in California, somewhere. Also in Appalachian, there are this type. It's pretty equally common as the mountain you see in Lamont, facing Lamont from the eastern looking west. Yeah, that shape also pretty shape. But this type of hill is give repeated landslide. I will show animation afterward. Anyway, their shared feature is they have collecting basin, they have like a parking area, those kind of a generic feature. Yeah, this is Montecito, the one called in 2018 called life loss and property loss. This one is it's Pakistan, from Pakistan side of the Himalaya, Tibetan plateau, that part. Vegetation is very good, covered. Also landslide mainly caused by the earthquake and falling storm, big storms. But you can still see the collecting area and parking area. Those can extend the gully. Yeah. The third specialty of the modern system is the treatment of the slopes after burning, especially after fresh burning. Anyone with gardening experience will know the humus soil, when you spring water on it, it's very hard to infiltrate into depth. But there are limitations. If you keep spraying it, it will eventually drains into depth. But for normal precipitation, like less than one inches total precipitation within 1 day, that's very hard to destabilize a well-vegetated slope, of less than 60 degrees steepness. But fair burning telling a different story. Not my direct research, but we have to believe others, research result. Diandong, he performed the literature review. Also, he himself performed the experiments of burning, undisturbed slope soil, like see how the hydrological characteristic of that piece of soil changed. They give very interesting parameterized scheme. I just borrowed into segment modern system. Yeah, here is an example. I not only graded sloping. Most important thing I will show here is the importance of QPF, quantitative precipitation forecasting. That's critical for increasing the prediction scale of debris flow. Hopefully, there are the audience from foothills lab. They will, the ones who run walk, will know the importance of QPF. I should say the setting. You know, this is the physical domain. I assume a slope like this part slope angle like for example 45 degrees, this part 30 degrees. Whatever shows in the parameter setting part is correct. Here I just give you an example. And uniformly 1 meter of granular material, for example, sand, coarse sand, not a fine sand, not clay sand, like a coarser sand, like you find on the slopes of the California, you know, not the soil slopes, you know, there are coarse sand slopes over there. You place uniformly on this slope, and you sprinkle it uniformly with certain precipitation strength. And after it getting saturated, it will starting creeping slide. I mean, it will accumulate to somewhere downslope here. Yes, stops with a rod with a nose, you know, with a trough. I mean, yeah. But in the simulation, that is a physical domain. What I displayed here is the numerical simulation domain. Like the upper panel is the thickness of the sliding material, they change. The second panel is like a overlap on the upper panel, is the velocity of the material which slides, you know. During the whole process, like when it's, creeping, and after it deceases, parked over there, it will diminish, the arrow will become like a point, the second panel. The third panel, you know, is either should repeat. Third panel, if you put into the actual physical domain, if I highlight, you will see some a little bit the material accumulate down the hill slope to that part. I use a very coarse resolution, you know, only 11 point in this hydrological domain. On this side, like is 101 grade threshold, this dimension. Yeah. So it's if you use like on supercomputer in a real case, it will be much smoother, the profile will be much smoother. But just here is just the case showing how segment three-dimensional model works in the entire process modeling. I use this very coarse resolution also because if I use the actual one, I cannot display here. You know, it must show on supercomputer. You know, that part of post diagnosis, MPI is not essential. TPU also works. The third experiment I showed here is natural shifting. Like you mix three types of particle, evenly, as like their volumetric percentage is only 1/3 each of them, 3 dimensions of of bead or glass bead, same material. You put it on top of the slope. There is a gate. You pull up the gate. The material will slide down the slope. The part over here. This is the yellow region, and also is corresponding to this area. And initially they are well mixed, evenly mixed. If you sample anywhere, you will find 1/3 is the biggest one, 1/3 is the middle-sized one, 1/3 is the smallest one. But after sliding and parking, at the bottom you will see the larger size beads, like runs faster, runs ahead of the low one. But during the process, there are interactions. They are bumping each other. There's a complex viscosity phenomena. How that eventually distributes. Segment can give a pretty realistic distribution of this. Like at the trailing tail, about 100% is funner size beads. In the middle part, it's like the distribution of the middle side is a yellow curve. The very coarse one. They are still not not totally separated, by natural gravity sorting. It's like still have a trail, but the percentage, like how much percentage the final mixture. This is important because the damage of landslide of debris flow, if you measure for the residential area, will depend on like where the boulders can, the big stones, the current slope they can reach, they can hit, Basically, the larger the boulder, the faster they can run. But what's the likelihood, like where they can pass, this can be determined are important. Like this kind of testing, the flag CD, the commercial one, failed. Failed. Right now, maybe successful. For real application, I still emphasize the importance of like warm, dry, Mediterranean climate, the wintertime precipitation is very important for California region. Also, I have to emphasize California is fortunate because it's a salad bowl and also crop production area for the entire nation. Their monitoring the data is plenty. Seismic measurement, remote sensing measurement, actual on-site survey. The documentary of the biomass loading, like how many tons of trees, pressing on the slope, those kind of data, all available. Thomas Dunn, helped a lot in pointing out where the data are, the resources. Thomas Dunn, previously, you see Barbara, professor right now retired, living in New Zealand. The last time I interacted with him in New Zealand, Southern Island. This I will skip, interested audience can contact me, The slide will be available, so here, available to any interested ones. As I said, the importance in setting up this primarily is fire burning effect and also this parameter setting. Process modeling system, the negative side is need a lot of data not required by statistical measures. We need run 3D model. Also, high resolution digital elevation maps for the interested region. The outline of the basin is automatically done, in the segment system. Not very important. I also put it here just means it's not the peak time of precipitation that occurs. It's just about the saturation and the runoff, peaks. That time it initiated the slide. Runoff is critically important for the initiation of debris flow. So, QPF is important in our ideal run. I did not fully mention it. If the rainfall is, it occurred initially at the lower part of the slope, we call nothing. Occurred at the upper part, we call one time of slide. But this packed material, if the next time the extreme precipitation happens in mid slope, can cause another following debris flow. That way, debris material, the fuel is not used one time; it can be repeatedly used. So this type of situation is dangerous because after first time debris flow, the people living over there may getting fatigued. They think things are over. And as long as no more fires, the slope may be safe for another 5 or 10 years. But the packed material, the next time precipitation occurred in the wrong place, will cause another round of debris flow. So QPF always is the top important factor affecting the prediction of this continental area. More, this just shows how the entire cycle, of the sliding material affected the region. Interested, audience can refer to my publication, published recently, but the work was done quite a long time ago. Many publications have a time delay. Also compared to the seismic measurement, they have a seismic measurement for other purpose, but fortunately recorded the landslide debris flow process for this case, for the 2019 January 8th, that case. We have comparison data. All these listed numbers are close to their measurement, also simulated by segment landslide. Model interface, not good looking, but physically important for monitoring, for diagnose the slopes stability. The second section will be brief, only, forgive me for 5-10 minutes, we will finish this. We usually think, this earthquake is very unpredictable, very complicated compared to our field. Actually, it's not that way. Potentially, it's because of lack of measurement, especially lack of remote sensing measurement, makes it mysterious. Right now, we have in the remote sensing age, things are changing quickly. Basically, it's nothing in the vacuum here, in the lower part is filled with mantle material, hot viscoplastic material filled everywhere. Ocean plate always beneath the ocean, continental plate, is what on land. It's not a coincidence, it's Curtin expert told me that's not a coincidence. That's a formation of the Earth. That's very necessary. Oceanic plate must be beneath the ocean, and always. For different portion of this upper tectonic plate, close to the mantle edge flow, it's like maybe called viscous kind of viscoplastic material. But most part of the upper mantle here is like a rigid material, and the interface between the oceanic plate, oceanic crust, plate and continental plate, their contaction is frictional contaction, just like a flamet against another flamet or your foot. The maximum friction is a control factor, preventing it getting sliding. Gradually, the mantle convection flow, like a conveyor belt, running this way, running this way underneath. Not a fluid, but it's creeping like ice, creeping. That kind of material. Which costs like very high, like 10 raised to the 17th particle second. That kind of material, close to solid. That force definitely is tremendous, or very tremendous. That's why the seismic cycle, co-seismic, pre-seismic, and after seismic, the cycle is basically controlled by this. Gravity, what I show here. Ideal case is like gravity from the loading of the continental plate, aiding the maximum friction. They work together against the mantle flow caused the stress, the compressing stress. Once these two fails, there is a co-seismic event, like an earthquake event. Afterwards, the cycle repeats. Without hydrological cycle, this process, for 100 years, the time scale will be very regular. Every 15 years, every 70 years, every 25 years, will be very regular. But we have a drought, extreme drought on a large spatial area. That kind of loading deloading, makes the earthquake happens, not that regular, not one time of one like a wet and dry cycle. It's a fatigue process, like a fatigue of the interface, like attrition, attrition producing granular material, weak the interaction, reduce the F maximum, Also, when the big drought happens, deloading happens, reduce the G, the gravity part. In that case, it's more likely to cause the earthquake event. I will show this. I will show you the result. Deloading, it's not 100% sure, because they have the mantle flow do not listen to this process, but very likely the deloading state is a trigger for big earthquake occurrence. Yeah, let's go back to what we have right now. We have more information in the remote sensor data. The GPS tells us how fast the velocity, the creeping speed of the plates are. Also, the radar, airborne radar, can detect some the plate geometry, From this, using numerical scheme, segment or some other scheme, we can infer, like using data simulation method, we can infer some of the granular material thickness, how many meters accumulated between the plates, like the weakening process of the interface. Also, more critically, we have the fingerprint of the gravity field. Currently, this is from Greece, it covers like a 10-year period. That's normal. The most important thing is they use the dual satellites, measuring their satellite difference when passing through an area. When the gravity field changes, for example, a big storm, big drought, cause the gravity, changes. The satellite will, the distance when at a different passing will be different. That way they deduce the gravity field. They have only 2 satellites. So the spatial resolution of these patterns are like 100 kilometer. That kind of spatial resolution. It's too close for direct measurement, direct use for earthquake prediction or simulation on prediction. But it gives indication, a good indication of when big earthquake occurs. For the Himalaya region, the earthquake always occurs when the gravity field is in near minimum. It's drought period. When it's drought, almost no case after 2005, the grace period. No that case of occurring during peak time, wet period of the region, is not happening. By the way, even bigger picture is the Indian plate and the Eurasia plate, subduct, underneath Eurasia one. But they are, fractured, many small faults over there. But region by region, all this applies. All this truly applies. Also, a fact is that you see a mountain means there is the gradual field is a deficit. Like, for example, you get bumped somewhere. Initially, you get a bump over there, but eventually you will have bone loss. The same thing for us. You see a mountain because that part is lighter. Your gravity measurement shows the background gravity is lighter in mountain area. In the ocean, ocean area is actually the gravity field is a strong gravity field over there. So the ocean area, you see the maximum in the background for the Grace scheme. Their inversion scheme, the spherical harmonic equation, the inverse result of that, still very useful. But at the end, I will show you. I should say I changed that part like significantly. If not called translational, it's not a gradual part change. But I use the similar scheme use multiple satellites. The more satellite pair, the better. Can greatly improve the gravity anomaly field to like a 10 kilometer, even down to 1 kilometer scale. That way, we can find it very useful in prediction of major earthquakes. This testify of this, including my message for the Morgan earthquake. Also, slightly before that, the Mediterranean earthquake. That one I try to contact their meteorological office even one day before the event. There are Google search record, of my effort try to give them the warning. Just the second day it occurred over there, unfortunately caused some loss. Same pattern, Peru is to the north of Chile, the two countries. Some of them happens during, ENSO El Nino period, some La Nina period. But the shared commonality is the gravity field minimum for that part of the country, that part of the affected country. It's affected by the ENSO cycle, but differently for this south-north segment of the Andes mountain. They happen, one is close, one is mostly follow the ENSO period, one is the La Nina period. But the shared commonality is when the gravity field is a minimum. This is the map of dry cycle dry frequency of the concerned earthquake, Malay subduction earthquake I produced in 2016. And the prediction of earthquake, back to that time I haven't developed my advanced scheme about using space, the satellites. Basically what I have access to the meteorological satellite. The meteorological satellite to fine-tune the gravity field. But back to that time I used second model with the existence, input from GPS and some other supplementary data, including aspects from UC University of Colorado here. They have a digital Earth model, very, very good, very useful for gravity field, called aspect. It's developed by CECU faculty in their group. I forgot the name. Sorry. I use their digital Earth as input to segment, because we are simulating like a portion of Earth, using a full spherical field. They use a Curtin field, even for Earth, they use a Curtin field, X, Y, Z. In segment is a spherical, fully spherical field, the spherical coordinate. That's my prediction. The file, if you dig out, if you see the slide, you will see it's not made today or yesterday, it's like years ago, 2010. I have some example. Like back to that time, I said this sector within 10 years will happen. It happened like last year. This one is what I mentioned. I try to Morocco. I try to contact their meteorological service to give a warning, but not without success. But it happened, the same color happened the same year. But it's still rough. The period is still come on. But the locational error, locational signature already showed up in the Grace gravity field signature back to that time. All this already happened mostly. There are some failure. I forgot. There are some failure. The Alaska one, I think, the so-called this area, the second model is made a mistake compared to timing or with the Andes, southern Andes area. But here, like roughly label this. But in segment give numerical output, there are still aspects to be expected, to improve. There are some mistake in this. But some of them, especially Japan and Taiwan, their earthquake really easy to with the grace like a gravity field normally, and especially with recent finer resolution gravity fields from multiple polar orbiter satellite, weather satellites. I'm pretty confident that all the earthquake in Japan and Philippines, Taiwan, that area, both time and location, I'm pretty confident within half a year period before it happens. I can see clearly with the data, with the needed data and the running model. I use this word, not overclaiming. It's truly maybe one of my happiest time in my career. It's like I developed this scheme. It's a lot of mathematics involved, physics involved. Even just for the four major actions, it's the weakest one, the gravity field. We only question about that. But the scheme, inversion of the spherical harmonic, that way is much more complicated than Grace currently used. For once, I consulted Dr. about the rebound, Earth rebound. That's the time I'm developing this scheme. That's like almost 2 years ago, I think. I consulted you about the Canadian faculty also previously worked here and collaborated here with the faculty here. Pewt here? The Paleo guy. They developed the bond. Their literature also helps, but that's one part. But my contribution is very significant in this part. When time permitting, I will write a paper and summarize my experience with this. Also present here, share with the interested colleagues here. Also, if someone interested, I will share this part of experience. And if you provide I needed information, the satellite, that information is like I do not have enough space to save it. The working place, either bureau or Curtin, they do not give me that resources. It's just like come and go. If you give constantly flow to that, we can use the segment constantly monitor earthquake tectonic process, not earthquake. Many times it's not. All type of earthquake, even subduction, major one, also the strike slip one, like California. In airplane we can see the trends. The St. Andrews, that one. They have very different mechanism of co-seismic, means the earthquake, the cosmic process. But they all have same thing during the process, seismic cycle, the gravity field fluctuation. They all have that kind of signature. So, for my scheme, when satellite is close to 15 or above, more than 15, this can be sub-kilometer scale. Like a 1 centimeter depth of water precipitation will show the clear signature. Precipitation one thing, some other process like also, as long as they have mass changes, will show up over there. That's my summary of the mitigation strategy. Still, I adhere to the same philosophy. As long as we improve our forecasting scale, build the confidence for audience, the mitigation will be a successful mitigation strategy and will be useful, beneficial for the society. Thanks for coming. Welcome.
I think we have been attending the seminar for long. If there's any question, then ask a question. No?
Also, the slide is free to access. Any question?
In this case, we just conclude our seminar and thanks Diandong one more time.
Thank all of you. 作者该在一个 hurry，所以这 slide 比较多一些，讲的比较慢一些。